All right, this slide or this set of notes is on work, energy, and power. So what is work? Work, and the symbol for work is going to be W, so that's pretty nice, is the energy transferred when a force, represented by the letter capital F, is applied to an object moving through a distance of d. Work is only done by the force parallel. That's why it has this weird little parallel thing. The component of force parallel to the distance the object moves. That is because these two things, force and distance, are vectors, so their direction does matter. They need to be moving in the same direction or parallel to each other. The SI unit, that's your metric system of work or energy, is the joule, and the symbol for joule is a capital J. And 1 joule is the same as 1 Newton meter, or Newton times meter. So we get to use metric system, which makes me happy. So here's an example. A student lifts a 50-pound, 50.0-pound ball 4.00 feet in 5.00 seconds. All those zeros are there just to show us that there are 3 significant figures. How many joules of work did the student complete? Well, work is force times distance. You'd have to be going in the same direction, of course, or parallel to each other. You take 50.0 pounds times 4.00 feet, which gives you 200 foot-pounds of work. But that is not using the metric system. That would be an English example. We want the SI unit, or metric system of calculating work. So we're going to have to convert these to metric measurements. So what's 50 pounds in the metric system? Well, we have a nice little conversion here. It would be on your equation sheet, but 50 pounds is equal to, well, 1 Newton for every 0.225 pounds, or 50 pounds being equal to 222.5 newtons. And then 4 feet, 1 meter is equal to 3.28 feet. So 4 feet is equal to 1.22 meters. Now we can use work and get an answer in joules, which is pretty much what's always used for energy. There isn't really a commonly used English system for energy. So force times distance, as long as they're parallel to each other, of 222.5 newtons times 1.22 meters, we get about, with some rounding to 3 digits, 271 joules of work. So energy itself is the ability to do work. Light, heat, mechanical, chemical, and electrical forms of energy can all be used to exert a force for a distance. And what's exciting is we are going to be doing one of these 3 things. What's probably not as exciting for you is it's not the roller coaster, and it's not the solar sail. Potential energy, stored energy. A lot of times we're talking about gravitational potential energy, but that's not the only type. The capacity or the ability to do work by virtue of position or configuration. What does that mean? Well, there's gravitational potential energy, and that's when you lift an object away from the Earth's surface. You've now given it potential energy because you can drop it or use that to do work. There's elastic energy, like stretching a rubber band. Electrical energy, electrical potential energy, is voltage when you have the switch open so that the circuit is not flowing. The electrons are not moving, but there's that voltage push that would send them moving if you close the switch. And then chemical energy, chemical potential energy, would be the energy that's in fuel before you burn them. Kinetic energy would be the energy of motion. Now, once things are moving, we can call it kinetic energy, which a body possesses because of its motion, which occurs anywhere from an atomic level to that of a whole organism. If we're talking about electrical kinetic energy, that's the energy when you close the switch. So now the electrons can move around. So it's kinetic. Thermal or heat energy would be the movement of molecules and electrons allowed. In engineering, though, thermal or heat energy is sometimes referred to as internal energy, if you ever see or hear that. Energy can be transformed from one type to another. So a few examples. Chemical energy to kinetic. Let's say you eat something. You have to consume food for energy. You convert it into motion by playing a sport or doing some sort of movement. Radiant to chemical. Sunlight takes radiant energy from the sun and then is converted into a chemical energy so that it can grow. And electrical to thermal. You can take this electrical energy in these power lines, convert it to thermal energy in an oven to cook a turkey. Types of renewable energy: biomass, hydropower, geothermal, wind, solar. To be renewable, it has to be consistently and rapidly, and maybe rapidly is the important part here, consistently and rapidly replenished by natural processes. Biomass, using a living or once living organism as fuel. Hydropower, from the movement of water. Geothermal, from heat within the earth. Wind, usually generate electricity. And solar, either for heat or photovoltaic to convert to electrical. Non-renewable stuff are things that cannot be replenished in a rapid manner. Sure, coal's being made over millions of years, but that's not very rapid. Same as natural gas, petroleum, uranium. These are going to be used up, and there's not much we can do to replace them. You've probably heard of conservation of energy, that it cannot be created or destroyed, but it can change from one form to the other. A lot of times we lose energy to heat, and we don't really lose it because it can't be destroyed, but it gets transformed into heat, and that heat goes away from the process or the system that we are interested in. So when an input is changed to an output energy, some of the output is usually heat, and that is not helping us do work usually. Lots of ways you can convert energy. So fossil fuels are chemical energies. We burn those to get heat. Sometimes we use that heat to turn things mechanically, and sometimes mechanical things can then spin and make electrical energy. That's how our coal-fired power plants work. Taking chemical energy, we're burning it, producing heat. That heat's going to turn a turbine, which is mechanical, and make electricity for us. Solar cells, a lot simpler. We just take sunlight. The energy from that sunlight can be converted into electrical. Wind turbines are taking the kinetic energy of the wind moving into mechanical energy of spinning a turbine into an electrical energy. Hydroelectric, there's some sort of gravitational potential energy. Usually the water is higher on one side. That spins a turbine. That's mechanical energy, which is converted into electrical. Nuclear, we're taking that nuclear potential energy as that atom breaks down, produces heat, spins a turbine, that's mechanical, which we convert into electrical. Within a vehicle, when we take this gasoline and we burn it, one of two things happen. Either it's converted into mechanical energy of moving stuff, or heat energy. Which one do we want? Well, we want to move the car, so that's mechanical energy. So the stuff that's lost as heat is not benefiting us. That's not a very efficient way to do things. As far as efficiency, it's got a goofy symbol. It's another Greek letter, eta. It looks like an N with a long tail on it. But efficiency is the percentage of the input energy, that's En, that is transformed to the output energy, that's E out. And usually it's in a percentage form, so eta equals input energy over or under output energy times 100. As far as What's a good efficiency? Well, our electrical power plants and our engines and cars are not very efficient at all, about 30%. If you can start to recoup some of that heat energy that's lost and take advantage of heating something, like if you're using that electrical power to heat a building, it can work as far up as 80%. So efficiency is trying to accomplish the same thing with less energy. Looking at this chart of energy consumption in the United States by source, you can notice a couple things. This column on the right here have some pretty high percentages, meaning that that's where we get a lot of our energy, and the ones on the left are pretty low percentages. Not much come from there. The other thing is, the one on the right, they're all non-renewable. The ones on the left are renewable. So over the next several years, we need to, as a country, move toward more of these on the left, because we're going to run out of the ones on the right. Power. So it has to do with energy. It's how fast do you burn energy, or how fast do you do work. So we can calculate power in two different ways. Either take the energy divided by the time that you're burning that energy, or take the work divided by the time that you do that work in. Work is abbreviated with a W. Watts are abbreviated with a W. So that can kind of be confusing, but work is a variable. So if you see it in a calculation like this, that's work. If it has a number next to it, that's a unit, that's a watt. That's the unit for power. Types of power: electrical uses electrical energy, mechanical power uses mechanical energy. And that can either be linear, back and forth, or rotary, which is in a circle. And then fluid power. Fluids we usually think of as gases, but they include gases and liquids. So if it's a liquid, it's hydraulic power, and if it's a gas, it's called pneumatic power. All right, so going back to our other example, if you notice, we never did use the 5 seconds before as far as the work, because work doesn't matter how much or how quickly you do it, it's just whether you do it or not. Power is how fast can you do that work. So how many watts of power did the student use to lift the ball since they did it in 5 seconds? Well, earlier on we calculated a work of 271 joules. So to get the power, we would take work divided by time, or 271 joules divided by 5 seconds. And that would give us 54.3 joules per second, or 54.3 watts. Yay!